In the vast cosmos where stars dance and galaxies spiral, we embark on a journey beyond our earthly existence. Since ancient times, humans have sought answers from the stars, fueling imagination and curiosity. Armed with technology, we explore the diversity and mystery within the cosmos. Telescopes, our time machines, unveil the secrets of space. From star birthplaces to black hole realms, our universe is a cacophony of wonders, each object telling a unique story. Fasten your seatbelts as we embark on an odyssey through the cosmos. Revelations, mysteries, and the magnificence of the universe await. Welcome to Beyond the Galaxies, exploring the cosmos. If you look out into the night sky with a telescope and see beyond what's visible to the naked eye, you'll see many imposter stars. Many of those points of light are galaxies, collections of millions to trillions of stars. Gravity holds stars, dust, and dark matter together in galaxies. Astronomers are still determining exactly how galaxies form. Hydrogen and helium made up almost all of space after the Big Bang. Some astronomers think that gravity pulled dust and gas together to form individual stars, and those stars drew closer together into collections that ultimately became galaxies. Others believe that the masses of future galaxies gravitated towards each other before the creation of their stars. Astronomers are also refining their techniques for measuring the mass of individual galaxies, such as three-dimensional movements of several galaxies, to better narrow down the Milky Way's mass. In the early 1900s, many astronomers thought the entire universe lay within our Milky Way. Others, such as Harlow Shapley, a scientist and head of the Harvard College Observatory, argued that the spiral-shaped blobs thought to be dust and gas were separate and called them island universes. It wasn't until 1924 that Edwin Hubble identified several special pulsing stars called Cepheid variables and realized they lay outside the known Milky Way span. These celestial objects were unique collections of stars at distances well beyond our home galaxy. After determining the distance to each galaxy, Hubble measured the Doppler shift, or how much light the galaxy's motion stretched out. He determined that galaxies around the Milky Way are moving away from us at terrific speeds. The farther away the galaxies are, the faster they are fleeing. Because of this, he determined that the universe was expanding, and years later astronomers decided that the expansion was accelerating. Most galaxies have black holes at their centers that can produce tremendous energy, which astronomers can see over great distances. Sometimes, a galaxy's central black hole is extremely large or active, even in relatively small galaxies. Its jets can accelerate material that is circling the black hole outward. Other galaxies may contain quasars, the most energetic bodies in the universe, at their core. The shape of galaxies determines their classification. Each type has different characteristics and a different history of evolution. Some, like the Milky Way, have arms spiraling outward around their center. Known as spiral galaxies, these groups make up most of the galaxies that astronomers can see. A spiral galaxy contains gas and dust, circle the center at hundreds of miles per second, creating their pinwheel shape. Some have a bar structure in the middle made of funneled dust and gas, known as barred spirals. The dust and gas in spiral galaxies consistently fuel the formation of new stars. Elliptical galaxies lack the spiral arms of their more flamboyant cousins. Their appearance ranges from circular to very stretched out. Elliptical galaxies have less dust than their spiral counterparts, so the star-making process has ended. Most of their stars are older. Although they make up a smaller portion of the visible galaxies, astronomers think that over half the galaxies in the universe are elliptical. The remaining 3% of the galaxies in the universe are known as irregular galaxies. They are neither round nor feature spiral arms. Their shapes lack specific definitions. The gravity of other galaxies has often affected them, stretching or warping them. Collisions or close calls with other galaxies can also deform their shapes. Instead of floating through space alone, galaxies form clusters. Some clusters contain over 1,000 galaxies, while others are much smaller. The Milky Way lies within the cluster known as the local group, which only has 50 galaxies. Occasionally, galaxies slam into one another, merging their stars and dust. This is an essential step in the evolution and growth of many galaxies. Astronomers released a study in late 2018 that depicted the collision of two supermassive black holes in the final stages of a galactic smash-up, marking the first instance of such a late galaxy collision. Individual stars generally don't collide in a galactic collision, but the influx of dust and gas bumps up the rate of star formation. In about 5 billion years, the Milky Way will collide with the Andromeda Galaxy, which has also experienced collisions in its ancient past. It's possible that its distinctive bulge emerged from the consumption of a sausage-shaped galaxy. The Andromeda Galaxy likely also devoured one of the Milky Way's early siblings. In recent years, astronomers have monitored galaxies and the influence of dark matter, an invisible substance to conventional telescope technology, on their evolution. Dark matter and dark energy are thought to make up most of the universe's mass and power, but their existence is difficult to prove because we can only see them through their effects on more conventional objects, like galaxies. In 2017, astronomers found 2 giant galaxies from the ancient universe formed in a sea of dark matter. The galaxies' massive size makes scientists wonder if they gradually grew more extensive over time, or if some other process might have been responsible. Astronomers discovered a group of galaxies orbiting in sync, a pattern that dark matter may explain, only a few months after that discovery. However, in 2018, a group of researchers discovered that a galaxy named NGC 1052 has about 400 times less dark matter than models would predict for an object of its size, challenging the dark matter theory and potentially altering galactic evolution models. However, the study results are controversial and still under debate. Periodic galactic surveys with increasingly advanced technology have allowed scientists to identify previously too faint galaxies to see and learn more about galactic evolution, size, and shape. For example, in 2017, the Multi-Unit Spectroscopic Explorer, MUSE, instrument on the European Southern Observatory's Very Large Telescope, revealed a group of 72 galaxies hiding in plain sight. In 2018, an image from the Hubble Space Telescope crammed in some 15,000 galaxies, providing an abundant hunting ground for future galactic studies. In the same year, researchers discovered hundreds of galaxies hidden behind a superenergetic black hole, which had previously obscured their presence. Hot young stars make up spiral galaxies, twisted collections of stars and gas that frequently have beautiful shapes. Most of the galaxies scientists have discovered so far are spiral galaxies, as opposed to the other 2 categories of galaxy shapes, elliptical and irregular. The Milky Way, which includes Earth and our solar system, is a prime example of a spiral galaxy. According to a 2010 Hubble Space Telescope survey, spiral galaxies make up roughly 72% of the galaxies scientists have observed. In most spiral galaxies, a flat, rotating disk of stars surrounds a central bulge. The bulge in the center comprises older, dimmer stars and is thought to contain a supermassive black hole. Approximately 2/3 of spiral galaxies, like the Milky Way, also have a bar structure through their center. The disk of stars orbiting the bulge separates into arms that circle the galaxy. These spiral arms contain a wealth of gas, dust, and younger stars that shine brightly before their quick demise. How the spiral arms form continues to puzzle scientists. One theory suggests the galaxy arms could result from density waves traveling through the outer disk. Encounters between galaxies could cause such waves, as the mass of the smaller galaxies could affect the structure of the more giant galaxies as the 2 combine. We believe that as spirals age, they evolve into elliptical galaxies. However, we need to clarify the characteristics of typical elliptical galaxies, as they consist of older, dimmer stars, making them more challenging to spot. One of the largest known spiral galaxies is NGC 6872, a whopping 52 light-years across from the tips of its outstretched spiral arms, about 5 times the size of the Milky Way. In 2017, astronomers discovered an 11-billion-year-old ancient spiral galaxy called A1689b11. Its discovery will help scientists understand how galaxies transition from highly chaotic, turbulent disks to more organized, thinner disks like the Milky Way. Although elliptical galaxies are the most abundant type of galaxies in the universe, younger, brighter collections of stars frequently outshine them due to their age and dim qualities. Elliptical galaxies lack the swirling arms of their more well-known siblings, spiral galaxies. Instead, they bear the rounded shape of an ellipse, a stretched-out circle. Cygnus A is one of the most famous elliptical galaxies, located roughly 600 million light-years from Earth. It is also a highly bright radio source. Astronomers and science fiction enthusiasts alike are familiar with Cygnus A, having featured it in Carl Sagan's 1985 novel Contact, which later inspired a Hollywood movie of the same name. In 1926, Edwin Hubble devised a system to classify galaxies. The Hubble sequence, or the Hubble tuning fork, organizes galaxies based on shape. This organization classifies elliptical galaxies based on their degree of stretching. Galaxies classified as E0 appear to be almost perfect circles. Remember, a circle is an ellipse, while those listed as E7 seem much longer than wide. The appearance of a galaxy depends on its position in the sky as viewed from Earth. For instance, a galaxy with the E7 shape but seen head-on would appear as an E0 because observers would not see its stretched shape, which lies behind it. Elliptical galaxies have a broader range in size than other types. The smallest are dwarf elliptical galaxies, which can be less than 10% of the size of the Milky Way. But ellipticals can also stretch to more than 1 million light-years across and contain more than 10 trillion stars. We classify M87, one of the universe's giant galaxies, as an E0 elliptical galaxy. Astronomers have identified more spiral galaxies than elliptical ones, but that's simply because spirals are easier to spot. While spiral galaxies are bright, elliptical galaxies are dim. Spiral galaxies are hotbeds of star formation, but elliptical galaxies are less prolific because they contain less gas and dust, which means fewer new and brighter stars are born. The existing stars inside an elliptical galaxy tend to be older, giving off more red light than younger stars. So why do astronomers think elliptical galaxies dominate the sky? Deep studies of specific regions of the sky reveal an increase in elliptical galaxies, and astronomers believe such counts are consistent throughout the universe. That may seem like a stupid reason, but it's very true. Because elliptical galaxies contain older stars and less gas, scientists think they are nearing the end of the evolutionary line for galaxies. The universe is violent, and collisions between galaxies are frequent. Indeed, the Milky Way is due to crash into the Andromeda Galaxy in a few billion years. When two spirals collide, they lose their familiar shape, morphing into less structured elliptical galaxies. A supermassive black hole is thought to lie at the center of these ancient galaxies. These gluttonous giants consume gas and dust and may play a role in the slower growth of elliptical galaxies. Elliptical galaxies originating from collisions typically surround clusters and groups of galaxies. The early universe spotted them less frequently, supporting the idea that they evolved from collisions later in a galaxy's life. Research in the past few years has revealed quite a bit about the evolution of elliptical galaxies. A 2014 study showed that supermassive black holes might stop star formation in elliptical galaxies, which would help explain why there are so few new stars in them. Previously, astronomers believed that ellipticals lacked the cold gas required for star formation, but the new study revealed that they contain abundant cold gas, which supermassive black holes in the region simply blast away. In 2015, researchers discovered that some compact ellipticals might lose most of their mass through galaxy interactions, which has significant implications for what happens when galaxies merge and collide. Galaxy mergers with ellipticals could produce weird hybrids like the Sombrero Galaxy. A 2012 NASA Spitzer Space Telescope examination found that Sombrero comprises one galaxy inside another. The study reclassified Sombrero as an elliptical galaxy with a flat disk inside it. Such examinations occasionally reclassify elliptical galaxies into other types, such as NGC 1382 in 2016. Scientists determined that the galaxy was not an oval, but a strange combination of cosmic pieces that came about through various mergers. Scientists are now interested in how many other similar galaxies reside in our universe. We don't know, but there could be thousands and possibly millions of Earth-like planets studying the dark latitudes of the Milky Way. Our galaxy could be thick with worlds that host life and intelligence. In this putative club of sentience, are we the newest arrivals? Although Homo sapiens have been plodding the planet for a few 100,000 years, our technical competence to build rockets and radios is only a century old. Anyone who's mastered 7th grade science knows that's a short time compared to the age of the Earth. You likely received encouragement as a student to create a paper strip chart depicting our planet's history, starting from its formation 4.6 billion years ago and encompassing bacteria, trilobites, dinosaurs and humans. If the chart ran the walls from the back of the classroom to the front blackboard, The representation of time since the invention of radio would be only 1/100th of a hair's width wide. If your chart began with the formation of the galaxy 13 billion years ago, the era of technological competence would be even thinner. So we're undoubtedly among the newest pledges in the frat house if club membership requires radio technology or better. That means that if we pick up a signal from extraterrestrials, we can be smugly confident that those broadcasters are far beyond our level. But there are other matters of relevance. How many club members exist, and how much more advanced would they be? If we want to estimate how many contemporary worlds have technically sophisticated inhabitants, we can begin with the Drake equation. This fabled formulation forecasts the number of high-tech galactic societies as the product of the rate at which they arise times their average lifetime. This is just like computing how many students are on campus at the local university by multiplying the number of new admissions by the average length of a college stay, close to 4 years. We know little about the average lifetime of technological societies other than that ours has, so far, managed to survive for a century. We also need to determine at what rate sentient societies spring up in the galaxy. However, we are certain that the frequency of star birth directly influences this rate. A greater flux of new stars will produce more planets with thinking beings. What is the star formation rate? The Milky Way has roughly 200 billion stars. The average rate over the last 13 billion years has been about 15 new stars yearly. However, this average rate needs to be more accurate. Anyone who's used a radio telescope to study galaxies knows that when you examine a big spiral like the Milky Way, you find that the total amount of interstellar gas is typically a few % of the mass of all the stars. Given that interstellar gas serves as the building block for stars, it's clear that there isn't much available today to build new ones. Sure, stars explode as they die, spewing some of their contents back into space. Even the sun will blow off steam as it heads for the stellar boneyard, but most of what's inside the sun will stay forever locked in by gravitation. The ingredients for new stars are sparse, and most of the stars our galaxy will ever make have already been made. Mary Barsony, a research scientist with the Space Science Institute, notes, "These days, the stellar birth rate in the Milky Way is only about 1 solar mass per year. The galaxy is not nearly as fertile as it once was. There seems to have been a real burst of star formation more than 10 billion years ago. Those early years were when the stellar population boomed. This must affect the roster for our club of intelligent beings. But how? There are two obvious possibilities. One is that intelligence is such a helpful attribute that technological societies last a long time, billions of years. Heck, trilobites lasted 500 million years and weren't even bright, by any reasonable standard. So maybe the Thinking Beings Club is home to old societies, and we're like preschoolers surrounded by grad students. The other possibility is that technology only survives for such short periods. While the galaxy may have spawned great civilizations in the distant past, they are largely extinct today. In this scenario, other club members are not quite ancient but need more supply. If either of these possibilities is true, it will only become apparent when we decode a signal from elsewhere. But the fact with which we began our discussion remains an indisputable fact. We are the new arrivals on the technological scene. Our strut and fret on the galactic stage have just started. A radio telescope that stands taller than the Statue of Liberty has detected an unexpectedly strong magnetic field as it appeared 6.5 billion years ago in a young galaxy. Astronomers have long thought that magnetic fields grow very gradually from slowly rotating galaxies over 5 billion to 10 billion years, but the robust field finding may force some rethinking. It measures at least 10 times greater than the average magnetic field in the Milky Way. This was a complete surprise, said Arthur Wolf, a physicist at the University of California, San Diego, who headed the team that hails from several UC campuses. The magnetic field we measured is at least an order of magnitude larger than the average value of the magnetic field detected in our galaxy. Magnetic fields help control the star formation rate and interstellar gas dynamics within galaxies. But until recently, astronomers knew very little about magnetic fields outside our galaxy. They had previously measured a weaker magnetic field in only one nearby galaxy. However, a different team of Swiss and American astronomers previously made indirect measurements, suggesting that the magnetic fields of young galaxies were as strong back in the early universe as they are in mature galaxies today. The Robert C. Byrd Green Bank Telescope, located in Greenbank, WA, and operated by the National Science Foundation's National Radio Astronomy Observatory, is the world's largest fully steerable radio telescope. The team behind the new study used it for their measurements. The finding represents the first direct measurement of an early galaxy's magnetic field. The young protogalaxy they probed, DLA 3C 286, is located in a region of the northern sky that is directly overhead during the spring in the northern hemisphere. Wolf said the earlier indirect measurements and his team's latest direct measurement of a distant galaxy's magnetic field do not necessarily doubt the current leading theory of magnetic field creation. The mean field dynamo model predicts that magnetic field strength started much weaker than they are today. Our results challenge the dynamo model, but they do not rule it out, he added. Rather, the strong field that we detect is in gas with little, if any, star formation, and an interesting implication is that the presence of the magnetic fields is an important reason why star formation is fragile in these types of protogalaxies. Wolf said his team has two other plausible explanations for what they observed. We speculate that we are seeing a field towards the central regions of a massive galaxy, since magnetic fields are known to be larger towards the centers of nearby galaxies, Wolf said. A shockwave from the collision between two galaxies may have amplified the field we detect. Astronomers hope to extend their magnetic field observations further to better understand their influence on the evolution of galaxies. The challenge now is to perform observations like these on galaxies throughout the universe, said J. Xavier Prochaska, another team member and a UC Santa Cruz astronomer. When the universe was young, countless dwarf galaxies formed, heating the universe and preventing the formation of more small galaxies, a new study suggests. The Big Bang, a theoretical beginning to the universe, is thought to have generated lots of hot stuff, electrons, hydrogen and helium ions. The material expanded rapidly. As space expanded, matter cooled, and the electrons and ions formed neutral atoms and absorbed surrounding light. This created a dark curtain throughout the space. We call this shadowy era the Dark Ages. The Dark Ages ended when the first stars and galaxies formed and began to shine. Their light stripped electrons from neutral gases in the universe, producing charged ions, a process known as reionization. During this time, the gas reionized and also heated. Hot gas does not easily clump together to form stars and galaxies. If gas is scorching, you need a very massive collection of it with a strong gravitational pull to attract enough additional matter to create a seed from which a galaxy can form. Before the period of reionization, galaxies containing only 100 million solar masses of material could form quickly. However, assembling more than 10 billion solar masses of material was necessary to form a galaxy after this period. Therefore, the theory states that the formation of dwarf galaxies, containing up to several billion stars, would have been suppressed during this era in favor of more massive collections of stars. Stuart Wythe from the University of Melbourne's School of Physics stated that while this was theoretically known, it lacked proof. We now have evidence that this occurred at the end of a period known as the Dark Ages, when the unstructured elements in space evolved under gravity into the universe we see today. Quasars, distant galaxies with bright cores powered by supermassive black holes, emitted light that the researchers used to determine the masses of early galaxies. In the early universe, clouds of hydrogen absorbed the light from quasars. More prominent and fewer galaxies lead to more variation in absorption across various lines of sight. As an analogy, suppose you're in a room where everybody is talking, Wythe explained. If this room is sparsely populated, then the background noise is louder in some parts than others. However, the background noise is the same everywhere if the room is crowded. The fact that we see fluctuations in the light from quasars implies that the early universe was more sparse than a crowded room. We found that fluctuations in light from quasars implied that the early universe was sparsely populated, Wythe said. A radio galaxy is a type of galaxy with giant regions of radio emissions that reach far beyond its visible structure. We explore them in more detail here. A radio galaxy dominates the sky over Earth in radio waves. These bright radio wave emissions come from billowing lobes of gas that extend far beyond the visible structure of the galaxy, often for millions of light years. These radio lobes usually occur in pairs and are created when the heart of a galaxy is home to a so-called active galactic nucleus, AGN, an extremely bright region dominated by a supermassive black hole that is superheating and feeding on the surrounding material, causing it to glow. According to the California Institute of Technology, Caltech, Around 15% to 20% of galaxies with AGNs are bright in radio waves and are classified as radio loud. We do not fully understand what distinguishes one AGN as radio loud and another as radio quiet, given that both types of AGNs emit similar wavelengths of light, from ultraviolet to X-rays. According to some research, radio galaxies almost exclusively take the form of giant elliptical galaxies, suggesting a connection between radio loudness and host galaxy type. The merger of two smaller galaxies could create these galaxies. The rotation of the central black hole could also be associated with radio emissions, potentially facilitating the formation of powerful jets. What are examples of radio galaxies? Famous examples of radio galaxies include Cygnus A, with a bright radio source that consists of two bright lobes of billowing gas and dust on either side of a galactic nucleus, Messier 87, with twin jets extending from a bright nucleus, and Centaurus A, an elliptical galaxy intersected by a lane of dust. There are two distinct types of radio galaxies, defined by differences in their optical emissions. Broad-line radio galaxies show light emissions from ionized oxygen, hydrogen, and silicon in their optical spectrum. Narrow-line radio galaxies are AGNs that lack broad-line emissions, but have narrow emission lines from hydrogen and triply ionized oxygen. According to modern cosmology and traditional galaxy formation models, dark matter halos form the foundation of galaxies. Over time, those halos pull in gases and material, eventually building up full-fledged galaxies. Disk galaxies, like our own Milky Way, form with prominent disks of stars and gas, and are thought to be created in a method known as hot mode galaxy formation, where gas falls inward towards the galaxy's central region, where it cools and condenses. This process is gradual and takes a long time. However, the newly discovered galaxy DLA 0817G, nicknamed the Wolf Disk, which scientists believe formed in the early universe, suggests that disk galaxies could form quickly. Marcel Nielman of the Max Planck Institute for Astronomy in Germany led a new study that used ALMA, the Atacama Large Millimeter-Submillimeter Array in Chile, to spot the Wolf Disk. They discovered that the object was a large, stable, rotating disk, clocking in at a whopping 70 billion times the mass of our Sun. In the new observations, the disk appears as if the universe were just 1.5 billion years old, or 10% of its current age. The disk seems extremely massive and stable for something so young. So how could such an enormous galaxy form so quickly, so early in the universe? Now, researchers suggest that the galaxy might have formed by a process known as cold mode accretion. They think the gas falling in towards the galaxy's center was cold, so because the gas didn't need time to cool down as it approached its center, the disk could cool down more rapidly. The Max Planck Institute says, the result provides valuable input for a present-day discussion about how galaxies form. However, astrophysicist Alfred Tiley noted in a Nature News and Views article accompanying this study that these findings are based on a single galaxy. He emphasized the need for more similar observations to validate this hypothesis. Astronomers have long suspected that most large galaxies form, at least in part, by acquiring smaller galaxies in dramatic cosmic mergers. New images from the Hubble Space Telescope support that view. Hubble photographed the Spiderweb galaxy, officially MRC 1138. It is 10.6 billion light-years away, and its light emanated when the universe was only a couple of billion years old. A growing galaxy cluster surrounds the Spiderweb galaxy, where dozens of young, tiny, star-forming galaxies are visible merging. Study leader George Miley from Leiden Observatory in the Netherlands said that the new Hubble image is the best example of how small galaxies merge to form large, massive ones. Gravity draws galaxies into the spiderweb from a sphere more than 100,000 light-years across. The galaxies race at hundreds of miles per hour. The Spiderweb galaxy is located in the southern constellation Hydra, the water snake, and is one of the most massive galaxies known. Segway 1 is 1,000 times more massive than the star cluster pictured above, but it is 50 times dimmer, indicating that dark matter must make up most of its mass. Astronomers have identified the least luminous galaxy known, but it's surprisingly massive. This is due to its abundance of invisible matter. Dark matter is mysterious, unseen stuff that permeates the universe. Astronomers know it's there because of the gravity it creates. Without invoking dark matter, theories can't explain how galaxies stay together. The galaxy, Segway 1, is one of about 24 small satellite galaxies orbiting our Milky Way galaxy. A separate study last month, reported in Science, found that all the known satellite galaxies are loaded with dark matter. But among them, Segway 1 is exceptional. It is 1 billion times less bright than the Milky Way, yet it's nearly 1,000 times more massive than its starlight would suggest. Segway 1 is the most extreme example of a galaxy that contains only a few hundred stars yet has a relatively large mass, said study leader Marla Geha, an assistant professor of astronomy at Yale University. Geha and her colleague Josh Simon at the California Institute of Technology have observed about half of the dwarf satellite galaxies that orbit the Milky Way. At first, we thought these objects, so faint and containing so few stars, to be globular clusters, tightly bound star clusters orbiting our host galaxy. However, by analysing the light coming from the objects using the Keck telescope in Hawaii, Geha and Simon showed that these objects are galaxies themselves, albeit very dim ones. The researchers expected these ultra-faint galaxies to have correspondingly low masses based solely on their emitted light. Instead, they discovered they are between 100 and 1,000 times more massive than they appear. Invisible dark matter, she said, must account for the difference, but that is wild speculation and conjecture based on nothing more than not having an answer. Although dark matter doesn't emit or absorb light, scientists can measure its gravitational effect on ordinary matter and believe it makes up about 85% of the total mass in the universe. Dark matter plays a crucial role in galaxy formation, possibly by forming clumps that stimulate star formation in a budding galaxy and adding to its overall matter, enabling it to attract other matter and galaxies inward during a growth by merger process. The Milky Way, for example, has, over billions of years, gobbled up many small galaxies, presumably including some like Segway 1. The researchers say that finding ultra-faint galaxies like Segway 1, which is so rife with dark matter, provides clues as to how galaxies form and evolve, especially at the most minor scales. These dwarf galaxies tell us a great deal about galaxy formation, Geha said. For example, different theories about how galaxies form predict different numbers of dwarf galaxies versus large galaxies, so just comparing numbers is significant. Astronomers have only recently discovered how prevalent these dwarf satellite galaxies are, thanks to projects like the Sloan Digital Sky Survey, which imaged large areas of the nighttime sky in greater detail than ever. In the past 2 years alone, the number of known dwarf galaxies orbiting the Milky Way has doubled from the dozen or so brightest discovered during the first half of the 20th century. Geha predicts astronomers will find even more as they sift through new data. The galaxies I now consider bright used to be the least luminous ones we knew about, she said. It's a new regime. This is a story that's just unfolding. Galaxies are vast collections of stars that populate our universe. But how many galaxies are there? Counting them seems like an impossible task. Sheer numbers are one problem. Once the count gets into the billions, it takes a while to add up. Another problem is the limitations of our instruments. To get the best view, a telescope must have a large aperture, the diameter of the primary mirror or lens, and be located above the atmosphere to avoid distortion from Earth's air. The most resonant example of this fact is the Hubble Extreme Deep Field, XDF, an image made by combining 10 years of photographs from the Hubble Space Telescope. According to NASA, the telescope watched a small patch of sky on repeat visits for 50 days. If you held your thumb at arm's length to cover the moon, the XDF area would be about the size of the head of a pin. By collecting faint light over many hours of observation, the XDF revealed thousands of galaxies, both nearby and very distant, making it the most profound image of the universe ever taken at that time. If that single spot contains thousands of galaxies, imagine the potential for finding thousands more elsewhere. While estimates among experts vary, Mario Livio, an astrophysicist at the Space Telescope Science Institute in Baltimore, Maryland, said an acceptable range is between 100 billion and 200 billion galaxies. The Astrophysical Journal expects the James Webb Space Telescope to reveal even more information about early galaxies in the universe. According to Livio, the Hubble Space Telescope has been successful in galaxy counting and estimation. Launched in 1990, a shuttle visit 1993 corrected the telescope's initial distortion on its primary mirror. Hubble also underwent several upgrades and service visits until the final shuttle mission there in May 2009. In 1995, astronomers pointed the telescope at what appeared to be an empty region of Ursa Major and collected 10 days' worth of observations. According to Weber State University, the result was an estimated 3,000 faint galaxies in a single frame, going as dim as 30th magnitude. For comparison, the North Star, or Polaris, is at about second magnitude. The Hubble Deep Field Image Composite was the farthest anyone had ever seen in the universe. As the Hubble telescope received upgrades to its instruments, astronomers repeated the experiment twice. In 2003 and 2004, scientists created the Hubble Ultra Deep Field, which, in a million-second exposure, revealed about 10,000 galaxies in a tiny spot in the constellation Fornax. In 2012, again using upgraded instruments, scientists used the telescope to look at a portion of the ultra-deep field. Even in this narrower field of view, astronomers could detect about 5,500 galaxies. Researchers dubbed this the extreme deep field. Hubble reveals an estimated 100 billion galaxies in the universe, but this number will likely increase to about 200 billion as space telescope technology improves. Regardless of the instrument, we estimate the number of galaxies to be the same. You take the area of the sky that the telescope, in this case Hubble, captured. Then, using the ratio of the sliver of the sky to the entire universe, you can determine the number of galaxies in the universe. This assumes that there is no large cosmic variance and that the universe is homogeneous, Livio said. We have good reasons to suspect that is the case. That is the cosmological principle. The principle dates back to Albert Einstein's theory of general relativity. Einstein said that gravity is a distortion of space and time. With that understanding, several scientists, including Einstein, tried to understand how gravity affected the universe. The simplest assumption to make is that if you viewed the universe's contents with sufficiently poor vision, they would appear roughly the same everywhere and in every direction, NASA stated. The matter in the universe is homogeneous and isotropic when averaged over huge scales. This is called the cosmological principle. One example of the cosmological principle at work is the cosmic microwave background, CMB, radiation that is a remnant of the universe's early stages after the Big Bang. Using instruments such as NASA's Wilkinson Microwave Anisotropy Probe, astronomers have found the CMB is virtually identical wherever one looks. Measurements of the universe's expansion, through watching galaxies race away from us, show that it is about 13.82 billion years old. However, as the universe gets older and more significant, galaxies will recede farther and farther from Earth. This will make it more challenging for them to see with telescopes. The universe is expanding faster than the speed of light, which does not violate Einstein's speed limit because the expansion is of the universe itself rather than objects traveling through the universe, and is accelerating. This is where the concept of the observable universe, the universe we can see, comes into play. Livio said that in 1 trillion to 2 trillion years, galaxies will be beyond what we can see from Earth. We can only see light from galaxies whose light has enough time to reach us, Livio said. It doesn't mean that's all there is in the universe, hence the definition of the observable universe. Galaxies also change over time. The Milky Way is on a collision course with the nearby Andromeda Galaxy, and both will merge in about 4 billion years. Later on, other galaxies in our local group, the galaxies closest to us, will eventually combine. Livio said residents of that future galaxy would have a much darker universe to observe. When civilization started, they would have no evidence that there was a universe with 100 billion galaxies, he said. They would not see the expansion. They would probably be unable to tell there was a Big Bang. Scientists speculate that our universe is not the only one. I personally think the evidence is flimsy, but some hardcore enthusiasts like to run with the idea. As the early universe inflated, some theories say that different pockets broke away and formed different universes. These places could expand at different rates, including other types of matter, and have physical laws different from our universes. There could be galaxies in these other universes if they exist, but we have no way right now of knowing for sure. Therefore, galaxies could be more significant than 200 billion when considering other universes. In our cosmos, Livio said, astronomers will be better able to refine the number with the launch of the James Webb Space Telescope, for which his institute will manage the mission operations and science. Hubble can peer back at galaxies that formed about 450 million years after the Big Bang. Using the James Webb Telescope, astronomers anticipate looking as far back as 200 million years after the Big Bang. The numbers are not going to change much, Livio added, pointing out that the first galaxies probably formed not too long before that. So a number like 200 billion galaxies is probably it for our observable universe. Astronomers are more interested in how galaxies reveal the universe's formation than in counting the number of galaxies in our universe. NASA asserts that galaxies illustrate the organization of matter in the universe, particularly on a large scale. Scientists are also interested in particle types and quantum mechanics, on the small side of the spectrum. Because Webb can look back to the universe's early days, its information will help scientists better understand the structures of the galaxies around us today. The James Webb Space Telescope is making considerable contributions to this subject. For those living under a rock for the last few years, we launched the James Webb Space Telescope on December 25, 2021. NASA said of Webb's mission, "By studying some of the earliest galaxies and comparing them to today's galaxies, we may be able to understand their growth and evolution. Webb will also allow scientists to gather data on the types of stars that existed in these very early galaxies." Through follow-up observations using spectroscopy of hundreds or thousands of galaxies, researchers will gain insight into the formation and accumulation of elements heavier than hydrogen throughout the ages. These studies will also reveal details about merging galaxies and shed light on the process of galaxy formation itself. According to NASA, Webb will answer a few critical questions about galaxies. How are galaxies formed? What gives them their shapes? How are the chemical elements distributed through the galaxies? How do the central black holes in galaxies influence their host galaxies? What happens when small and large galaxies collide or join together? Scientists are also interested in the role that dark matter plays in the assembly of galaxies. While some of the universe is visible in forms such as galaxies or stars, dark matter makes up most of it, about 80%. While dark matter is invisible in wavelengths of light or through emissions of energy, studies of galaxies dating back to the 1950s indicated there was far more mass present in them than what was visible to the naked eye. NASA stated, "Computer model scientists have developed to understand galaxy formation indicate that dark matter merges and clumps together to create galaxies. Dark matter is the framework of the universe. The visible matter we see collects inside this scaffolding in the form of stars and galaxies. Dark matter clumps together due to the formation of small objects that attract larger ones." Webb's powerful mirrors will allow scientists to look at galaxy formation up close, including the role of dark matter. While this investigation doesn't directly answer how many galaxies there are in the universe, it does help scientists better understand the processes behind the galaxies we see, which better informs models about galactic populations. A new study has found that galaxies like ours harbour mysterious magnetic fields that build up much faster than scientists realized. By analyzing the light coming from distant galaxies early in the universe's history, astronomers showed that these galaxies developed magnetic fields much sooner than expected. The finding may force scientists to rethink how magnetic fields grow inside galaxies. The magnetic fields in these galaxies were very strong, at least as strong as they are today, at a time when the universe's age was only 1/3 of its current age, said researcher Francesco Miniati of the Swiss Federal Institute of Technology. That puts strong constraints on the evolution of magnetic fields. Faraway light sources illuminating the galaxies under study helped make the discovery. Miniati and his colleagues used the European Southern Observatory to observe the distant bright objects, called quasars, in visible and radio light. Quasars are the central regions of some galaxies where supermassive black holes generate tremendous emissions across the electromagnetic spectrum, from radio waves to visible light and X-rays. The radio waves the researchers observed often showed signs of passing through a magnetic field. When a typical galaxy lay between Earth and the quasar, the magnetic field signature on the light was most potent. This informed the researchers that the foreground galaxies, not the quasars, held their responsible magnetic fields. "We were surprised that we could measure this so cleanly, and that these galaxies had such strong magnetic fields early on," Miniati told Space.com. "Only a few galaxies have convincingly demonstrated this in the past. With this measurement, We could show that all regular galaxies have these strong magnetic fields early on. Scientists think galactic magnetic fields start from tiny magnetic seeds, perhaps created inside stars or quasars, and are amplified over time as the turbulent movement of galactic gas, stirred up by stellar explosions, and the galaxy's rotation caused the magnetic fields to grow. This standard picture, however, can only account for strong magnetic fields that build up slowly over time. The new finding implies that scientists must develop an improved explanation for how magnetic fields build up inside galaxies in the young universe, such as those Miniati and his team observed. Surprisingly, the mature galaxy in the early universe suggests that galaxies form faster than we thought. A distant galaxy in the newborn universe resembles a grown adult when it should look like a small child. New findings suggest that galaxies may evolve far more rapidly than previously thought. Galaxies come in a variety of shapes, colours and sizes. Much remains a mystery about how galaxies formed in the early universe and how they evolved mature features such as rotating disks and central bulges of tightly packed stars. To peer that far back in time, astronomers need to look at light from distant galaxies, but such targets are often too dim to see well. In the new study, researchers focused on the galaxy ALES 073-1. The starlight they detected from this galaxy came from 12.5 billion years ago, when the universe was 1.2 billion years old, about 10% of its current age, according to study lead author Federico Lelli, an astrophysicist at Cardiff University in Wales. Massive disks found in the early universe challenge galaxy formation theories. Just 1.5 billion years after the Big Bang, a massive rotating disk galaxy known as DLA 0817G, also known as the Wolf Disk, formed. ALMA, Chile's Atacama Large Millimeter Array, made the discovery. Using the Atacama Large Millimeter Array, ALMA in Chile, the scientists analysed high-quality images they successfully collected of ALES 073-1's dust and gas. They used this data to model how matter was concentrated in the galaxy and calculate its motions. Unexpectedly, the researchers discovered the galaxy possessed a rotating disk and a central bulge. They also found signs that it may even include the same kind of spiral arms that mature galaxies, such as the Milky Way, have extended from their cores. This galaxy looks like a grown adult, but it should just be a little child, Lelli said. At least 073. One's core also generated more energy than stars can explain. Prior work has suggested that such an active galactic nucleus, AGN, hints at the presence of a supermassive black hole millions to billions of times the Sun's mass. Previously, researchers thought central bulges formed slowly over time due to gravitational instabilities within a galaxy or mergers between galaxies. ALES 073. One, however, was able to form a big bulge, making up about half of its stars in less than 1.2 billion years, Lelli said. This young galaxy appears surprisingly mature. This map shows the gas motion in the galaxy, less than 073. 1. The gas in blue is moving towards us, while the gas in red is moving away, suggesting the galaxy is rotating. According to earlier research, galaxies forming in the primordial universe should generally be chaotic, turbulent, and largely unstructured due to their intense activity, such as consuming gas from their surroundings and forming stars at extremely high rates. Lelli stated that the orderly structure within ALES 073-1 contradicts these expectations. These findings suggest that galaxies can form mature features such as disks and bulges far more quickly and efficiently than previously thought. Structures like bulges, regular rotating disks, and possibly spiral arms must form in less than 1 billion years, which is a tall order for current models of galaxy formation, Lelli said. Lelli said that in the future, scientists aim to collect similar high-quality images for a dozen or so more galaxies from the same cosmic epoch. These new observations will establish whether galaxies like ALES 073-1 are the rule or the exception in the primordial universe, Lelli said. The universe has between 100 billion and 200 billion galaxies. With numbers that large, you can bet that some real weirdos are out there. Beyond our Milky Way are galaxies shaped like jellyfish, galaxies that consume other galaxies and seem to lack the dark matter that pervades the rest of the universe. Located in the constellation Triangulum Australe, Galaxy ESO 137 001 looks amazingly like a jellyfish swimming amid a sea of stars. The galaxy is a barred spiral galaxy. Together, its stars form a spiral shape with a bar-shaped center, with a twist, streamers of stars that seem to drift like jellyfish tentacles. According to NASA, these stars are forming inside a tail of dust and gas, invisible to the naked eye, that streams off ESO 137 001. This formation process is a mystery, as the gases in the tail should be too hot for star formation. What is the matter with missing matter? In 2018, the Hubble Space Telescope spied something never seen before, a galaxy with almost no dark matter. This discovery immediately raised red flags. Dark matter is mysterious and interacts with gravity but not with light. It makes up more of the total matter in the universe than the matter we can see, so finding a galaxy without any was bizarre, to say the least. A year later, scientific sleuths solved the mystery. The galaxy, NGC 1052 DF2, was not 65 million light-years away, as initially believed. It's only about 42 million light-years away. Researchers reported on March 14, 2019, in the journal Monthly Notices of the Royal Astronomical Society. That change in distance completely alters the calculations for the galaxy's mass. All in all, it's a standard galaxy, and the universe makes sense again. The massive disc-shaped galaxy MAX 2129, one spins twice as fast as the Milky Way, but it's still not nearly as active. Hubble observations of the distant galaxy reveal that it hasn't made stars for 10 billion years. MAX 2129, one is known as a dead galaxy because stars no longer form there. The discovery of this galaxy was a head-scratcher. Scientists believed that galaxies of this sort had formed by merging with smaller galaxies over time. But MAX 2129, one's stars didn't form from these sorts of explosive mergers. They started early on in the disk of the original galaxy. The findings, published in Nature in 2017, suggest that dead galaxies internally rearrange their structure as they age, rather than changing shape, because they combine with other galaxies. As if zombie galaxies weren't spooky enough, some are giant cannibals. The Andromeda Galaxy, Earth's most prominent neighbour, has been devouring smaller galaxies for at least 10 billion years, according to 2019 research. In another 4.5 billion years, the Andromeda and the Milky Way galaxy will collide, although it's unclear who will devour whom in that cosmic pile-up. Unfortunately, Earthlings will not be around to see this clash play out, as our sun is heating up and will likely make life on Earth impossible between 1 billion and 5 billion years from now. 300 million light-years away, an enormous tadpole swims through space. This tadpole galaxy has a whopping 500,000 light-years long tail and is 10 times longer than the Milky Way. What created this odd galactic shape? Researchers reported a cosmic collision in the journal Monthly Notices of the Royal Astronomical Society in 2018. Two-disk galaxies pulled on a smaller dwarf galaxy, clumping the stars on one end into a head and leaving the others to stream out in a long tail. This arrangement is for a limited time only, though. In a few billion years, the galaxies will merge with others in their vicinity to create one single galaxy. If it still needs to be obvious, galaxies frequently interact with one another, squeezing their neighbours into new shapes, stealing stars, and carrying on with other shenanigans. The brightest known galaxy in the universe is one of these thieves. In 2018, scientists announced that they'd observed the galaxy W 22460526, sucking up half the mass of 3 nearby galaxies. Astronomers could observe streamers of mass connecting the galaxies, at least as they were doing that more than 12 billion years ago when that light began its journey towards Earth. The observation is the most distant direct snapshot of galactic cannibalism, and the only known example of a galaxy siphoning off more than one neighbour at a time. Possibly the cutest named galaxy ever, Little Cub sits in the constellation of Ursa Major. This dwarf galaxy has been largely dormant since the Big Bang, meaning it might contain molecules unchanged since just moments after the rapid expansion of the universe 13.7 billion years ago. Little Cub is also doomed. Its larger neighbour, the Milky Way-like galaxy NGC 3359, is consuming it. Still, the opportunity to watch NGC 3359 strip the star-forming gases from Little Cub, is valuable to science because astronomers may be able to measure the signatures of those early universe molecules before they're gone. Against the void of space, galaxy ESO 381, 12 is blooming. This galaxy, 270 million light-years from Earth, is in the constellation Centaurus. It's a lenticular galaxy, a hybrid between a spiral galaxy like the Milky Way and a stretched-out elliptical galaxy. What makes ESO 381, 12 really strange, though, are the uneven, petal-like blooms that ghost outward from the central galactic body. Astronomers are still determining what causes these structures, or the clusters of stars that orbit on the galaxy's edges. The blooms are shockwaves from a relatively recent galactic collision that gave the galaxy new fuel for star formation. Messier 83 is a large, photogenic spiral galaxy with a bar-shaped center, similar to the Milky Way. It sits 15 million light-years away in the constellation Hydra. Messier 83 is weird in a couple of ways. First, it appears to have a double nucleus at its center, perhaps the mark of two supermassive black holes holding the galaxy together, or maybe the effect of a lopsided disk of stars orbiting a single central black hole. Second, Messier 83 is a supernova supersite. Astronomers have directly observed 6 of these stellar explosions in the galaxy, along with remnants of 300 more. This puts Messier 83 in second place for supernovas, as only the galaxy NGC 6946 has produced more observable supernovas, with 9. Even though the image resembles a psychedelic dandelion puff more than a cosmological phenomenon, botany has nothing to do with this Hubble Space Telescope snapshot. You're seeing a galaxy, the smudge at the lower right, beginning to pass behind a star, the dandelion-looking spiky sphere. The galaxy is nicknamed the Vermin Galaxy by some scientists because its light gets in the way of studying the closer star and its system. In 2020, the star will entirely obscure the galaxy. Before then, scientists can study the spectra of light as the galaxy transforms behind the star, perhaps gleaning some information about the debris around the star from the light that makes its way through. Ever feel like you're being watched? The spiral galaxy. IC 2163 disk peers into space with an enormous eye. This eye-shaped feature is a massive stream of stars and dust, produced when IC 2163, at right in the image, brushed against another spiral galaxy, NGC 2207, left. These ocular features last only a few tens of millions of years. Astronomer Michelle Kaufman, who reported the discovery in 2016, said in a statement, "Discovering one is a unique opportunity, as it represents a mere blip in the lifespan of a galaxy." The researchers found that the gases of the eye feature race towards the center of IC 2163 at 62 miles per second, 100 kilometers per second, before crashing like a wave on the shore. They become more chaotic and slow as they move towards the galaxy's center. The deceleration causes the gas to pile up and compress, which could set the stage for forming new stars. A supermassive black hole at the center of most galaxies probably serves as their anchor. A few, though, contain not one but 2 black holes. One of these is NGC 7674, a spiral galaxy whose center boasts a pair of black holes a mere light-year apart. The galaxy, 400 million miles from Earth, probably collected the spare black hole during a collision and merger with another galaxy. The only other galaxy with 2 black holes at its heart is a supermassive galaxy called 040-2+379. When you're a galaxy, you either consume other galaxies or die. Galaxy NGC 1277 chose the latter. First reported in 2018, it is a mere 240 million light-years from Earth. It hasn't formed new stars for about 10 billion years, making it a dead galaxy. Astronomers believe that NGC 1277 became stunted because it moved too fast to gobble up other galaxies in its gravitational pull. It travels through space at about 2 million miles per hour, or 3.2 million kilometers per h. Without gas and dust from alien galaxies, NGC 1277 no longer forms stars. Some astronomers think most galaxies started looking like NGC 1277, evolving spirals and other shapes only through later mergers. Most galaxies scientists observe appear to be moving away from Earth because space is still expanding. It's not Messier 90, though. This spiral galaxy is about 60 million light-years away, moving towards the Milky Way. The skewed light from Messier 90 towards the blue end of the spectrum allows astronomers to detect this movement. Redshift occurs when objects move away from Earth, resulting in a reddening of their weak emissions. Messier 90 is part of a large group of galaxies called the Virgo cluster. NASA states that you can view it in May from the northern hemisphere using a telescope or binoculars between Virgo and Leo's constellations. The Milky Way may be home, but that doesn't make it any less weird. It turns out that it has been poaching galaxies from its neighbours. Astronomers reported in October 2019 that the Large Magellanic Cloud, a galaxy about 163,000 light-years away from our own, once orbited 4 dwarf galaxies and 2 large galaxies, Carina and Fornax. All 6 of these galaxies now belong in the Milky Way's orbit. As a bonus, the study also found that the Large Magellanic Cloud is stranger than previously believed. It hosts many tiny dwarf galaxies, some so faint that they don't even have stars, only dark matter. The evolution of intelligent life on Earth may not have been a cosmic fluke, but part of a pattern of interdependence between planets and the galactic environment around them. According to a new study challenging a widely held anti-ET argument, intelligent life beyond Earth might not be as dim a hope as many scientists think. Many skeptics tout an idea called the anthropic argument that claims extraterrestrial intelligence must be scarce because the time it takes for intelligent life to evolve is, on average, much longer than the portion of a star's existence that is conducive to such life. But astrobiologist Milan M. Sirkovich and colleagues say they've found a flaw in that reasoning. Astrophysicist Brandon Carter proposed the anthropic argument in 1983, building on his pioneering work on anthropic principles in the 1970s, on the assumption that the 2 timescales, the life cycle of a star and the time required for the evolution of living and intelligent creatures, are entirely independent. If this is true, Carter argued, it's doubtful that these 2 windows of possibility would last roughly the same time and co-occur. Sirkovich asserts that we need to update that mode of thinking. In fact, he asserts that the relevant timescales are deeply intertwined and not independent. There are many different ways in which planets in our solar system are not isolated, Sirkovich said. We must not regard habitable planets as closed boxes. If you abandon that assumption of independence, you have a whole new background in which you can set up various models of astrobiological development. Sirkovich points to gamma-ray bursts, nearby supernovae, and perturbations of comet clouds as possible events in the astrophysical environment of the star that can influence the biological environment on a planet. For example, when a star travels through one of the dense spiral arms of the Milky Way, higher levels of interstellar electromagnetic radiation and cosmic rays due to the higher frequency of star-forming regions and supernova explosions could disrupt its own development, as well as that of its planets. Sirkovich argues that all these connections work together to rule out Carter's independence and link the life of a star to the evolution of life on a planet. In the case of the Earth, the 2 timescales have lined up fortuitously to enable life. Our Sun is about 4.6 billion years old, and Earth is just slightly younger, at 4.5 billion years old. It is believed that our planet formed the first, most basic cells about 3.8 billion years ago, but the Homo genus, to which humans belong, did not appear until about 2.5 million years ago. Modern humans are only about 200,000 years old. For more than 80% of the Sun's existence, life has existed in some form on Earth. The timescales of biology and astrophysics have been favourably aligned in our case. According to the anthropic argument, this coincidence means that Earth and its life are unique. However, Sirkovich thinks the 2 timescales may not have overlapped by chance. Instead, they may be part of a complex history involving the interdependence of the Earth system with the rest of the Milky Way. Cosmic events like gamma-ray bursts or nearby supernovae could reset the astrobiological clock to give a planet and star a chance to sync up and try again to produce life. Gamma-ray bursts are mysterious explosions that release vast amounts of energy, either as dying explosions of supermassive stars, like Eta Carinae, or collisions of neutron stars in close binary systems. If a gamma-ray burst occurred in a large region near a planetary system, it might cause a flash of radiation and possibly cosmic ray jets that could disrupt life on planets. Supernova explosions, though not as energetic as gamma-ray bursts, but much more frequent overall, pack quite a wallop and could shock any nearby planets. A gamma-ray burst won't affect whether life will begin at some particular point in time, but it would affect how quickly life develops or takes hold by causing changes in atmospheric chemistry on the planet, Sirkovich said. We can interpret this as resetting astrobiological clocks on each habitable planet in the Milky Way. This idea leads to a new way of thinking about the origin of life. Instead of a long, gradual evolution, a catastrophic event could spur the development of a complex biosphere and intelligent beings, much like the evolutionary theory of punctuated equilibrium predicts that species will undergo long periods of slow evolution, punctuated by brief bouts of drastic change. For instance, paleontologists say that humans evolved to our present state only thanks to an asteroid impact 65 million years ago that wiped out the planet's primary predator, the dinosaur. Throughout its history, Earth has experienced many mass extinctions with various causes. While extinctions wipe out life, they are also a reset button that alters the environment and allows other types of life to emerge. This is part of a complex set of astrobiological histories that Sirkovich and colleagues dubbed the astrobiological landscape of our galaxy. The speed of evolution is very variable, Sirkovich said. There is no reason to think that life on Earth has only one origin. It is quite possible that there were several beginnings of life on Earth. Sirkovich also notes that the evolution of intelligent life can occur slower or faster in different settings and does not need to follow the astrobiological history of the Milky Way. Large-scale correlations might cause more such CT targets to be contemporary with us than expected based on planetary age distribution only, Sirkovich said.